Hello, Math 1224. This is Dr. P with Lesson Launch 21, Global Approximation. So this video and the next one and the next class, they're going to cover section 10.5 of the Hughes-Halleck Calculus textbook, which is about global approximation of periodic functions. So in this video, I just want to give a brief synopsis of what that means, and then we're going to dig into most of the central arguments and techniques in class. So I just want to recall that throughout this chapter, we've been using Taylor polynomials and Taylor series to approximate, well, in the case of Taylor polynomials approximate, Taylor series represent exactly functions on the real line. So for example, might have a function like f of x equals e to the x, and we might approximate that using polynomials, and we discovered that the greater the degree of the polynomial we were allowed to use, the better the approximation we get. So for example, a polynomial of degree 0 would give an approximation that has the right value at x equals 0, for example, but isn't necessarily a very good approximation anyplace else. And then a degree 1 Taylor approximation, well, that would allow us to do a little bit better. We could get something with the same value at x equals 0 and the same slope, but it might deviate greatly from the function after that. And we got progressively better functions, or approximations, like a degree 2 approximation, or maybe a degree 3 approximation, and I'm just sort of guessing what these would all look like. But one thing that we noticed is that every approximation was pretty good in some neighborhood around x equals 0. So there might be some neighborhood around there where the polynomial is very close in value to the actual function. But there is always this issue where, especially as x approached negative infinity, the tail of that polynomial function would behave very differently from the tail of this exponential function, which has a horizontal asymptote. There is no polynomial that has a horizontal asymptote as x goes to negative infinity. So this is a case of what we call local approximation. Local approximation because it's very good near a point, but any finite polynomial approximation would have had major flaws as x went to negative infinity. You can only count on it for so long, in other words. In this section, we're going to talk about a method of global approximation using periodic functions, but the problem is it really only works well, in my opinion, on periodic functions. So for example, suppose I give you some really off-the-wall periodic function. In this section, we're going to deal almost all the time with periodic functions that have period 2 pi, just like your basic trigonometric functions, sine and cosine. These functions are going to have period 2 pi. The entire technique can be adjusted if your period is something other than 2 pi, but we're not going to mess with that too much. Okay, so suppose I have this function I want to approximate, and I'm not going to lie, this function is kind of wild. It's a little wacky, all right? But suppose I have this, I call this the Charlie Brown function. You'll see why in just a second. So I'm going to make this periodic. By the way, do you know what it means for a function to be periodic? I should probably say something about that. It means that if I look at any interval that spans a width of 2 pi on the input axis, the function's behavior there repeats after this and also before this. So in other words, I could take the interval from 0 to 2 pi, and the behavior of the function on that interval will copy exactly the behavior between negative 2 pi and 0. And again, from 2 pi to 4 pi, very same behavior. So if I were to continue this function, it would have to look like this in order to be periodic, okay? So that's the idea of what it means for a function to be periodic. Is actually, there's an algebraic way of putting it that I think puts it a little more succinctly, although it can be a little bit hard to unravel sometimes. The idea is that f of x plus 2 pi is equal to f of x for every, that symbol means for every, x in the real number system. Okay, so in other words, input values that are 2 pi apart always yield the same output value. Okay, so anyway, you'll notice that this function, kind of weird, it is continuous, but it is not differentiable. For example, it's not differentiable here, nor here, nor here, nor here. Okay, second derivatives, third derivatives, you can forget about there. I mean, it'll have them on these linear segments. On the linear segments, all derivatives exist, and most of them are 0. But at these little cusps here, the first derivative, the second derivative, all your derivatives are undefined. Now, that's a contrast with what we did in the previous sections when we were talking about exponential functions, or really any function on which we were trying to get a Taylor approximation. Those functions were differentiable, they were twice differentiable, they were differentiable as many times as you wanted. And that was really key to using Taylor's method, because Taylor's method required us to find all the derivatives of that function, right? In this case, not going to be able to do that so well. That's okay. We're going to do something different anyway. We're going to approximate this using a combination of periodic functions, namely the trig functions, the basic trig functions, sine and cosine, variations of those, okay? So here's how this is going to work. This is my function f of x here. We're going to call that f of x. And what I'm going to do is I'm going to create something called a Fourier polynomial. That is an R at the end. It's a French name, Fourier polynomial. And here's how it's going to look. Now, I should mention it's not going to be a polynomial in the traditional sense of the word polynomial. I guess you could say this thing identifies as polynomial, and that's perfectly fine. So this polynomial, it's going to be some combination of periodic functions. It's going to start with a constant, a naught. Any constant function is periodic because it certainly satisfies this rule here. Okay, constants are periodic. And then it's going to consist of this wacky stuff. So it's going to have some term a1 cosine of x, there we go, plus b1 sine of x, plus a2 cosine of 2x, plus b2 sine of 2x, plus a3 cosine of 3x. You'll notice that at every value of the subscript, there's two terms. There's a cosine term and a sine term. b3 sine of 3x. And we're going to keep marching on like this. There's going to be one for every one of these, for every natural number, until I get to some specified n. an cosine of nx plus bn sine of nx. And then we're going to stop. Okay, now we're also going to talk about Fourier series, which go on forever. So these would not stop it, and they would just go on forever. But this is a Fourier polynomial. Again, not exactly polynomial, but you could think of it as a sum of terms where each term sort of follows a certain rule. That you could think of that as being kind of like polynomial. This is called a Fourier polynomial of degree n. All right, and that's what we're going to use to approximate this function. Now, by now you should be thinking, okay, wait a minute, what the heck? Because I know what these functions look like. I know what their graphs look like. Like sine of x, for example, its graph just sort of, I'm just going to draw a sketch with no axes here. Sine of x looks like this. It's curvy, it's wavy, right? And then cosine of x sort of goes like this. So I'm just going to sketch out various ones of these here. This cosine of x is going to go like this. It's going to start at 1, and then, boy, my sketches are not very good right now. It's going to go like this, I think. Let's see. Coordinating these is kind of hard. Before you knock my work here, just try doing this off the cuff. Okay, that's a cosine curve. Has the same shape as the sine curve. It's just translated. Okay. Now, what about this term? What about sine of 2x? What is that going to look like? Well, that looks like a sine wave, but it's been compressed horizontally by a factor of 2. So, see if I can get this as accurate as possible here. Okay, those are going to be the zeros. I'm just mapping out where the zeros are going to be, and then off we go to the races here. That's a sine of 2x. Okay, but what you notice about all these is that they're curvy. They're not pointy like this function. And really, no polynomial that I put together is going to fix that exactly. Every function every Fourier polynomial I use to approximate this is going to be curvy, not pointy. But that's okay. You can be curvy and still be a pretty good approximation for this function. So a really high degree Fourier polynomial approximation for this thing. Now, this is just me sort of sketching this and giving you a preview rather than an algorithm for how to find it at this stage. But it's going to look something kind of like this, all right? Okay, so it's going to have some waviness. Yeah, it's going to bop around a little bit. Okay, now at this point you really should have no reason at all to believe me. I just want to, highlight that here. Okay, it's going to approximate that function kind of like that. And again, this is a cartoon. It's not in any way accurate. And the green curve I drew certainly isn't periodic. I just sort of randomly drew something. But here's the idea I'm trying to capture here, okay? Is that these curves, as these wavelengths get narrow and narrower, like for a very high value of n, your sine curve is going to look like this. And by the way, the other thing that's going on that I should highlight, now those should all be the same amplitude. I'm sort of drawing that poorly there. But the other thing to notice is each of these has a coefficient. Okay, so you could have a sine curve like this sine of x here. That could be sort of the dominant term, and that could go like this. And you know, when you look at it, that kind of looks like what I want here. It's not too far off of what I want. Okay, if this, I didn't say where the amplitude of this triangle wave was, but let's say it's 1, then gosh, that sine of 1x is not so bad. But it's still inaccurate through these straight line segments here. Okay? But if I introduce a smaller coefficient here and sort of damp that down, then these higher degree terms, oops, need a pen there. These higher degree terms, they're going to be smaller, and they're going to interfere with this bigger wave in a way that might help the approximation a little bit. So instead of seeing this, if you add this curve and this curve together, or those two functions together, you might get something like this. Wibble, wobble, wibble, wobble, wibble, wobble. And what I drew there may be better or may be worse for this triangle wave function over here, but my point is that if we pick exactly the right combination of these, especially these terms, I think these are the ones that we really want to key in on, then we might get a pretty good global approximation for this function, an approximation that is never very far off of this blue curve, and it'll probably get better and better as we allow the degree of this polynomial to increase. So we're going to get into the details of that in class, but I wanted to do whatever intro I could to foreshadow what's going to be happening. In the next video, we're going to do a little technical result that'll be helpful to us, so stay tuned.